Now let's take a look at the chain rule for multivariable functions. So first, let's take a step back and let's recall the chain rule from single variable calculus. So in the case where you have f is some function of some expression of x, which here I'm going to call u of x, the derivative of that can be written this way. So d dx of f of u of x can be written as df du times du dx. So that, again, should be familiar from single variable calculus. So now we're going to try to bring it back to where we have multivariable functions. So first of all, what would a composed function scenario look like here? Well, suppose we have z equals f of xy, but then in addition, x and y themselves are both functions of another variable, which we're going to call t. So we can say x is some function of t, which is often written x of t, and then y is y of t. So altogether, we can write this out as saying z equals f of x of t, comma, y of t. So now we want to ask, what is the derivative of the outermost function f with respect to the innermost variable t? So in other words, df dt. What is that? Well, there's two ways to sort of think about what that might be. Number one, we could take the expression f written in x and y, but then we also know x and y in terms of t, so just plug those expressions in, and then f becomes a function of t, z equals f of t. And now it'd be very easy to find df dt. The other way to do this is to use what would be the chain rule. So now let's talk about what that chain rule might be. Okay. So to come up with this rule, we're going to start with something that I've talked about previously, which is the differential df. So we've seen previously, we know that df equals partial derivative df dx times dx plus partial df dy times dy. And if you want to refresh yourself, you can go back to my discussion about differentials to see where that expression comes from. So once we have that, it's pretty easy to get to df dt. So clearly you can just divide both sides by dt, and you immediately get the chain rule that we need. So df dt equals partial df dx times dx dt plus partial df dy times dy dt. And once you understand differentials, it's easy to get this chain rule. And remember that this can also be written in our alternate notation for partial derivatives. So df dt equals d sub x of f dx times dx dt plus d sub y of f dy times dy dt. So let's apply this to a problem. So let's start with the function z equals f of xy, which is 2xy plus cos y. And we've got x equals 6t squared and y equals ln t. And then let's find df dt at t equals 1. So remember I mentioned there are two different methods. So let's take a look at how each of those methods would work. So method 1, where we're just going to re-express in terms of t. So we now, just plugging in, we get that the function f is just 2 times 6t squared times ln t plus cosine of ln t. And now it's very straightforward. This is just a simple single variable calculus. Just calculate df dt. And you get, first using the product rule, so 24t times ln t plus 12t squared times 1 over t. And then minus, now using single variable calculus chain rule, minus sine of ln t times 1 over t. And then we're given the initial value t, or at the point t equals 1, so just plug that in, and you wind up with 12. So now let's take a look at how it would work if we try to apply the chain rule. So once again, here's the chain rule, and now we just need to figure out what these things are. Okay. So calculating the chain rule here, df dx is 2y, and dx dt is 12t. Df dy would be 2x minus sine y, and then dy dt would be 1 over t. So now we've got to plug in, but you'll notice we've got an expression in terms of x and y and t. We've only been given a value for t equals 1. However, x and y are both functions of t, so we can figure out what they need to be. So t equals 1, we can plug in to find x must be 6, and then y equals ln of 1, which is 0. So now we've got all three of those values. So at t equals 1, we know that df dt equals 2 times 0 times 12 times 1, plus 2 times 6 minus sine of 0, all of that, and then that times 1 over 1. And work it out, and you get 12. Okay. So these are the two different methods we're going to work on. So the first method obviously just reduces it to doing single variable calculus. We're going to, but you should be well familiar with that. So we're going to work on this new method using the chain rule. And then later on, very soon, we're going to see a case where you cannot just use the plug-in and do everything in terms of t method. You really do have to use the chain rule. There's no option. Okay. But for now, let's work on this problem and work on it using the chain rule. So z equals x cubed y plus 3x squared y to the 1.7. But we've also got x equals sine of 2t and y equals cos t. And now let's find dz dt at t equals 0. So one of the first things I'm going to do is I'm actually going to start off by figuring out if t equals 0, then what are my x and y values? I'm just going to jot this down on the side. So we know that x is going to be sine of 2 times 0. That's just sine of 0, so that's going to be 0. And then y is going to be cosine of 0, so that's just 1. So later on when I need my values for x and y, I have them. Okay, so now let's get back to it. So we need to find dz dt, and so by the chain rule, we know that that's partial dz dx times dx dt plus partial dz dy times dy dt. Okay, so now we just need to figure out what these things are and then plug in. So dz dx, 3x squared y plus 6x y to the 1.7 times dx dt. So dx dt is just going to be cosine of 2t and then multiplied by 2. I'll stick the 2 in front. Oops. Plus dz dy. That's going to be x cubed plus, bringing that down, I'll have 5.1 x squared y to the 0.7. So there's my dz dy, and now I just need dy dt. dy dt is just going to be negative sine t. Okay, so there's my dz dt. So now I need dz dt at my individual point. So dz dt at t equals 1, sorry, at t equals 0. And now I just plug in my t value, my x value, and my y value. You get 3, 0 squared times 1, plus 6, 0, 1 to the 1.7. And all that times 2 cosine 2 times 0, plus 0 cubed plus 5.1, 0 squared 1, 0.7 times negative sine of 0. So you plug it in, you work all that out, and you wind up with 0 plus 0, and it all just works out to be 0. So it simplifies pretty easily. Okay. So there is a nice classic example of how to apply the chain rule, where you've got z is a function of x and y, and each of those are functions of t. Okay, so now we're going to look at a problem that represents two things. First of all, it's an application, and second of all, we're going to find that there is no way to actually rewrite things in terms of what we're calling our t variable, our sort of like our inner variable. So let's take a look at this problem. Okay, so it's a physics application, and I'll start you off by telling you all the physics you need to know. So it's about an electrical circuit, and Ohm's law relates voltage V, which in physics is the potential ability to move charge measured in volts, the current I, which is the speed at which charge is moving, that's coulombs per second, which is called amps, and the resistance R, which is the wire's tendency to resist charge moving through it, and that's measured in ohms. And the rule is V equals I times R. So if the current is 4 amps, and the rate of change of the current is -1 amp per minute, the resistance R is 300 ohms, the rate of resistance is -5 ohms per minute. First, let's find the voltage right now, and then let's find the rate of change of the voltage, and that would be in volts per minute. Okay. So part A, of course, super easy. We just use V equals IR. So at this particular moment, let's see. So we're trying to find the voltage. So V equals I times R. So at this moment, we know that the current I is 4, resistance R is 300. So we know that right now the V is 1200 volts. Okay. Next. So once again, we're going to start with V equals I times R, and we're going to look at what the question is asking for. The question is asking for what is the rate of change of the voltage at this particular moment in volts per minute. So in volts per minute, how do we write down the rate of change at a particular instant? What it's asking for is rate of change in voltage per time. So what it's asking for is dV dt. So notice that, so that tells us that the variable we want to take derivative with respect to is going to be t. Now notice that we don't have expressions that we can differentiate. So we're actually going to have to go ahead and just use the formula for the chain rule, and then we're going to see that that'll give us something that we can solve out. So in terms of the chain rule, what do we have? We know that V is a function of two things. What are those things? I and R. And then I and R, well, those are just like V has to be a function of T, so it changes, T changes. Same thing with current I and resistance R. Both of those are changing as time changes. And of course, we also know that that's true because what's given? What's given, for example, is that the rate of change of the current is -1 amp per minute. So in fact, that's given information. So what's the given information? The given information is that the rate of change of the current is dI dt, and that's -1. Also given information, the rate of change of the resistance is -5 ohms per minute. So that's resistance per time. So we know that's dR dt. And at this particular moment, that's -5. And so I should mention that that's not dr dt as a function, that's dr dt at this particular moment. Okay, so we've got those two facts. Let me just put them off to the side for a second. Oopsie. Huh. So let me take those two facts, and if I get this to work, put this off to the side for a second. There we go. Okay. So we know that we know that we're going to need derivatives in terms of t. So we can now write out the chain rule on v equals IR. So we know that dv dt, which is the thing that we want, has to be dv di times, di dt plus dv dr times dr dt. So the one thing we do have a function for is v. V equals I times r. So we can calculate the derivatives of v. So derivative of v with respect to I, v equals IR, that's just r. And we don't know anything about the function I, so we're just going to leave that as di dt. And again, derivative dv dr, we can calculate that. That is just I. And we don't know anything about the function r, so we just leave this as dr dt. But look at what we've got. We've now got expressions r, di dt, I, and dr dt. All of those are for this particular moment. We're given values for all of those. So at this particular moment, we know that r equals 300, and we know that di dt is -1, and at this particular moment, we know that I is 4, and at this particular moment, we know that dr dt is -5. So put that all together, and you get -320, and the units we're using are volts per minute. And so again, let me emphasize the fact that up until here, we've got a general expression for dv dt, but then subsequent to that, we're saying what is dv dt at our particular moment. And we could plug in values for that. So that was a look at how to use the chain rule, but the version of the chain rule for multivariable functions. So we look specifically at where you have z, some function, for example, is a function of two variables, say x and y, but x and y themselves are each a function of another variable, for example, t. Now, of course, in the application, it was a little different. Our function was called v. That was a function of two variables, which were I and R, and then I and R themselves were a function of one variable, which in that application was t. You might imagine how to extend this if your big function, say v, was say a function of three variables, and then all of those were functions of t. We're not going to go into that at this time. Okay.